Femi Okay.
And I'm Malika Bilal, and you're in the stream.
Today, the search for the dark side, where our scientists what dark matter research could explain about our universe.
This topic has definitely piqued the curiosity of our online community, so keep your dark matter questions coming. Chat them to us live on YouTube or via Twitter.
Uncovering the world of dark particles could be the key to understanding the nature of matter, gravity, and what is holding the universe together. But after decades of research, scientists have yet to find direct evidence of what some call the dark sector, where an unknown matter exhibits gravitational force but cannot otherwise be detected. It is one of the biggest mysteries in physics, and though invisible, the dark sector is believed to make up about 96% of the universe and the billions of galaxies within it.
So today we'll speak to scientists on why dark matter matters. With us on set is Alexandra Eman, an astrophysicist, observational cosmologist, and a fellow at Stanford University. Her current research focuses on mapping dark matter in space. In Rhode Island, Stefan Alexander. He's a Brown University professor, theoretical physicist, cosmologist, musician, and author of the book, The Jazz of Physics, the secret link between music and the structure of the universe. Katie Mack is a theoretical astrophysicist. Her work focuses on studying the early universe through physics and astronomical observations. She's an assistant professor at North Carolina State University, from where she joins us. And in Rome, Mauro Raggi, a particle physicist at Sapienza University and the National Institute of Nuclear Physics, Rome. He is part of a dark matter experiment that is looking for a fifth universal force dubbed the dark force. Welcome to the stream, everyone.
Hello, scientists. So good to have you here. So I'm going to start with Jana Levine. She's a professor of physics and astronomy at Barnard College, and she was given this challenge. Talk about dark matter as if you're having coffee with a friend, and this is what she came up with.
Dark matter is really a name we give as a proxy to indicate stuff that we don't know what it is, really. It's just to say there's something out there, we can't see it, but we can tell it's out there because of the effect it has on space and time around it. So it's gravitationally affecting the universe, but it's not visible to us. Some people think it should be called invisible matter because light passes right through it. It's literally invisible.
Stefan, you describe what you do as mostly what I do is wrong. So you're studying something, you don't know what it is, and you're trying to work that out. What is that like?
It's like being on a planet with no sound and being asked to compose music.
Oh, almost impossible, because you have to ask yourself, what is music? Right?
And
wow.
Yeah, what does it sound like?
Oh my goodness. So even the very word or the phrase dark matter, that just means we don't know what it is. Yeah?
Yes.
Yeah.
Well, we have, again, indirect evidence, of course, on a multiple ways of knowing that it exists. So we do know it exists, we just don't know much about its identity.
Uh-huh. Katie?
Yeah, I think invisible matter is a great way to put it. We have a lot of ways of seeing that there has to be some extra matter there, because we see the effects of its gravity in a lot of different places, on small scales, at galaxies, and large scales for the whole universe, but we just don't know what it's made of. So it's some kind of invisible stuff. It has lots of different effects. It changes the whole large-scale structure of the universe, how galaxies and clusters of galaxies come together, but we can't see it directly. We can only see that, there's something weird going on in the things that we can see. They're moving in strange ways. It's even bending the shape of space itself. But we just need to figure out what it is, like if it's a new particle, what that particle is, what it's actually made of fundamentally.
Well, in the pursuit of trying to figure out what it is, I'm going to add two more voices to this conversation. So the first is from Jay, who actually, when this person heard that we were doing a science topic, tweeted us this GIF. Finally, I'm here for this. Someone, they're really excited about this topic, and here is why, because they actually know a lot about what they're talking about. Jay says it is a hypothetical form of matter that is thought to account for most of the matter in the universe. It's made up of elements that don't emit light or energy, hence the name dark matter. Here's one more thought on that from someone who isn't in the sciences. This is Hin Mackey. She says, I studied humanities and social sciences, so I don't know what dark matter actually is, but I like what it represents, an invisible force that affects every nanosecond of our lives while we go about blindly unaware of its existence. So Alexandra, I'm going to go to you with these two definitions there. But what I like about Hin's is that she seems to be saying it affects all of us and we just don't know or care enough.
Yeah, so dark matter really played this crucial role in the story of our universe, as it makes up most of, as they correctly said, most of the matter in the universe. It means that a less consequential thing is that it means that every picture that we see of a galaxy is a little bit distorted. As Katie said, the presence of the dark matter distorts the light that we see.
So Mara, as a field of physics, when you are planning what you do next, how do you do it knowing that you know so little?
So what we do is to choose an hypothesis. So when you are an experimentalist, you cannot play with many hypotheses because we have to build an object, which takes time and costs money, so you have to choose. So you choose your chance. You give trust to some theory and you say, okay, I'll try with this. Then you study the theory, you understand what are the phenomenology you can expect from this candidate dark matter, and then you try building an experiment to detect it and to bring, maybe shine some light to our theory guys to work on. So that's what we try to do.
Stefan, I see you nodding there.
Yes, that's exactly the point, which is that because we don't know what dark matter is, we have to, it's like, you know, if you have a ghost haunting your house, you don't really know what the ghost is, but you might project some sort of personality onto the ghost and go looking for a personality. Likewise, we are familiar with particles in the rest of nature. So one of the things we might want to, you know, tune our experiments for is to look for a dark particle. However, there are certain anomalies, certain mismatches that may suggest that the dark matter may not actually be a particle and may actually force us to even revisit the very foundations of physics itself.
So it's a bit of a different perspective if you're an observational cosmologist, because you don't have to set up your experiment. Your experiment is the universe, and it's set up waiting for you to make observations. And so I think Katie and I, as observational cosmologists, will look at that a bit differently. We can take images of millions of galaxies and use that to try and understand dark matter from a totally different perspective.
So when we talk about, Katie, I'll go to you with this, because when we talk about making those observations, I wanted to bring in this comment from Emma, who says, dark matter is the name given to all of the missing matter in the universe. It's dark because we can't see it. It doesn't interact with light. So if we can't see it, how then do we know it exists? So how do you go about making observations for something that you can't quite grasp?
Yeah, so the work that I do is kind of actually halfway between the observations and theory. So I think about what the theories are, and I think about what the observations can do, and I try and find ways to bring those together. So the way you do it is you think about, if this particle did exist, if there is some kind of massive thing out there, what would it do to the matter around it? What would it do to the stars, the galaxies, to space itself? And then you look for signatures of that. You look in the sky and see, you know, is that space distorted? And you'd figure out the space is distorted because the light would be sort of bending weird. You'd see multiple images of galaxies where you should expect only one. You would look at galaxies and see that the rotations of the galaxies are not what you would expect if all of the matter is just what you can see. And so we see that galaxies are rotating too fast, which suggests there's some extra stuff holding them together, some extra gravity. There's lots of things like that where in lots of different areas we see things that really point to something that we can't see has gravity, that's holding things together, that's making things move around strangely, that's changing the shape of space that we can see as the light is passing through that space. And all of it, when we bring it together, tells a pretty consistent picture. There are a couple of places on the edges where we don't know exactly what's going on, but for the most part, when we look at all these different observations, we say, you know, if we just add one more thing in our universe that has some gravity but we can't see it, everything kind of falls into place.
And there's work that you're doing and research that you're doing all of the time. Mara, I'm coming straight to you. Just hold tight for a moment. This is a headline from The Guardian in their particle physics section. Scientists hunt mysterious dark force to explain a hidden realm of the cosmos. That was a recent headline. And then let me just go to a report that Neve Barker from Al Jazeera just filed just recently. And Neve went to Italy's National Institute of Nuclear Physics. He met you, Mauro, there. This is what he was looking at.
And this is where it begins, with a particle accelerator and a theory.
We'll just select positron particles, positons, so positive particles.
A beam of positively charged subatomic particles called positrons is fired at a target, a diamond wafer 1/10 of a millimeter thick.
And this is the diamond mounted.
When the positive particles smash into the negative electrons in the diamond wafer, they produce photons, light. But every now and again, the collision between positrons and electrons could produce a dark photon, the invisible twin of ordinary light, dark matter.
We are trying to have a link in between this huge hidden world to our small known world.
Is it fair to call this the bridge between the seen and the unseen?
It could be, yes. Dark photon, it's a way of, like photon allows you to see.
Mauro, your workplace is so much more fascinating than mine. I'm fascinated by that. So, in a nutshell, can you explain what it is that you're doing that is making headlines right now? It's very newsworthy.
So, what we're doing is, as I was saying, we choose an hypothesis. The hypothesis is that there is a particle called dark photon, which is linking the dark sector, so dark matter, to visible matter. And if this exists, it has to interact with ordinary matter, for example, electrons and positrons. So we're using a beam of antimatter, namely anti-electrons that we call positrons, and we smash it on a thin diamond target to find electron in it. So matter is done of electron and protons. So if our positron meet an electron, they will annihilate, so they will be destroyed, generating energy. Out of this energy, we could generate a known photon, so a visible photon, and a dark photon. So this is what we were trying to do, generating dark photons using particles. Because we think that dark matter is a particle.
Have you done it yet?
We already started doing it,
yeah.
But we will not be able to see immediately the effect, because this interaction, if it's there, is very rare. Otherwise, this dark matter will be not dark. We will be seeing dark photon continuously.
And if I could jump in, an interesting thing about this experiment is it's looking for dark matter, but it's also making use of antimatter, which is a totally different thing. So antimatter is it's sort of a kind of regular matter. We've detected lots of antimatter particles. A particle of nature like the electron will have an antimatter partner, which in this case is a positron, and it's sort of like a mirror image of it. And if these two particles come together, they can annihilate and create a bunch of energy. And so this is something that's useful in these kinds of experiments. So you shoot a whole bunch of positrons at your target, and then you can get these annihilations, and that helps with the signal. So it's a cool experiment because you get to use both of these sort of mysterious things. This antimatter, which is not really mysterious to physicists, but it sounds cool to everybody else, and then looking for dark matter, which is this mysterious thing to everybody, this invisible hidden thing we don't understand yet.
So I'm glad that you brought up the mirror image, both Katie and Mauro there, and the idea that this is mysterious to some people, because I wanted to bring in this comment we got live on YouTube. Kat Lego says, I feel like I'm going to the first day of lecture. I know a bit of knowledge, but not enough to comment in class. So they are watching silently, but I want to help elucidate what we are talking about by sharing a video comment from someone who talks about that mirror image you both were talking about. This is Priya. She's an astrophysicist at Yale University, and this is what she told the stream about the Padme experiment.
Given the difficulty in detecting this dark matter particle, there have been some new theoretical ideas, one of which suggests that much like our universe, where we see all these particles, there might be a mirror universe, a dark sector. So that would mean that for every real particle that we see, there would be a counterpart in the dark sector. So the Padme experiment is trying to look for such a signal.
So Stefan there, my ears perked up at the idea that there might be a mirror universe. Can you pick up on that?
Yeah, in fact, I developed some early work on that mirror universe, basically models of particle physics that necessarily have mirror particles. I wrote some early papers on that, some of my colleagues as well, which is different than the idea of supersymmetry, which is another form of having a mirror, except the mirror particle is a force carrier. The mirror particle will be a matter particle in supersymmetry. But actually,
Stefan, I'm just going to pretend I knew exactly what you said right there. I'm just going to nod, and then everybody will think, wow, Femi knows so much.
But I want to actually add another perspective,
go ahead.
Which is that there are, when I say anomalies associated with dark matter, there's other experiments that shows that, for example, there's a universal, when a galaxy rotates, right, it's accelerating. The velocity is changing its direction, so it's accelerating. One of the universal things we see with galaxies, right, spiral galaxies, is that they're all accelerating. This is an observation at a very particular rate, right? And again, it's something that the dark matter particle models cannot explain. There's another thing where we see that the visible matter traces, all right, the dark matter, and I'm not calling it a particle yet.
So the visible matter tracing the dark matter is the perspective that I can bring, where if we look at really distant galaxies, their shapes are a bit distorted compared to what they are in reality. And that's because massive structures along the way distort light from those faraway galaxies as it travels all the way to Earth on our telescope. So the light path actually gets bent. And that means that all pictures that we take of galaxies are a little bit distorted because of this dark matter. So the dark matter is influencing the visible light that we can see. And that's an effect called weak gravitational lensing, which it doesn't give us a dark matter particle, but it can tell us where the dark matter is, how much dark matter there is, how clumpy it is.
So when I'm thinking about this sort of mirror image of the universe, could there be another stream show that's going on that is incredibly smarter than this one, or happening in another universe? Is that possible? Is that what we're talking about? Or is it something completely different?
So I think that's more of a question for the theorists. As an observational cosmologist, I really stick to what
I'm not touching that one.
We're not speculating. We use exactly what we...
Katie?
Well, we do have some ways of putting constraints on those kinds of ideas. So it's possible that there's a whole sector, a whole bunch of different particles that are all invisible to us that interact with each other. But if they interacted in exactly the same way that regular matter particles do, then they would form disks like galaxies that we see. They would flatten out in certain ways that we don't see. So we know from the way we can map the way that space is bending that dark matter collects in kind of more of a blobby structure than regular matter. It doesn't form these kind of flattened out disks like galaxies. And so there are certain ways that we can say that if there is a whole other sector, and if there are these interactions, they're kind of not as strong or not quite in the same sort of way that things interact in our sort of visible world.
But that's a very interesting analogy that Katie made, the scaffolding idea, because that's really what dark matter is to a cosmologist. It makes the scaffolding of our universe, and then it's like you put Christmas lights around it, and that's the galaxies that we can see.
And I'm glad you're answering that question because we got this, Maura, I'll go to you, but we got this question from someone on the same wavelength as Femi. Harit says, if we can have dark matter all around us and we can't properly quantify it, does it mean it's possible for there to be an alternate reality or a parallel universe without ever being aware it's there at all? So I think we got an answer to that, but Modo, here as we move on, I want you to talk about this because Yusuf here says, this is nonsense, which upon investigation yields little for the well-being of humanity. Come on, AJ Stream, stick to culture and geopolitical social affairs and leave the hard, quote-unquote, sciences to others. Modo, this is your life's work. Why does it matter?
It does matter, because if you think to it, we just know very few of what the universe is made of, because we are just less than 20% of the matter which is around the universe. So this does mean that we think to know a lot, but really we know nothing about what the universe is made of. And this is, of course, a challenge that we have to pursue, because we cannot stay there not knowing why all the galaxies are the form we observe. We cannot stay there without knowing why our galaxy has the form that we observe. And if we don't understand what dark matter is, we will never understand what we observe in the universe, which is very, very important for humanity, I think.
And as
because
Katie
politics
said,
goes around, but universe is universe since billions of years.
And as Katie said, there are multiple observations that tell us that there is this missing mass that is dark matter. It isn't, something speculative. This is something that is making up most of the matter in our universe. It's not.
Stefan? I want to quote the great Nobel laureate Abdus Salam. I think it's a very important question. And that quotation, he won a Nobel Prize actually for the weak interact, for the standard model. And he said, scientific inquiry is a common heritage of humanity. I mean, it's our basic it's a universal thing to human culture that we have this intrinsic curiosity. And this scientific enterprise to, continue to discover these mysteries is something that actually brings us together across the world, actually. So I think it's a very viable question that needs to be addressed also at that level.
Stefan, I'm so glad that you mentioned the Nobel Prize, because it would be remiss of us if we didn't talk about Vera Rubin. Dark matter and Vera Rubin, like, I don't know, toast and butter, fish and chips, right? How do we do that? We can't have one without the other. Have a look here on Popular Science in memory of Vera Rubin, the woman who the Nobel Prize forgot. Her work was really impressive and so important. Katie, can you tell us a little bit more about her?
Yeah, so what she did is she was looking at how spiral galaxies rotate. So in a spiral galaxy like our own, the stars go around the center of the galaxy and they sort of circle the center of the galaxy over millions of years. And so she was looking at that rotation and found that the stars were going so fast around these galaxies that they should have just flown out. The galaxy should have ripped itself apart, but they were held in by something extra. Some extra gravity was holding these stars into those galaxies. And that work showing that all of these galaxies were rotating too fast, that the rotation for the most distant stars and the nearby stars were kind of the same magnitude, that showed that there really needed to be this extra stuff. And there were other people who looked at similar things and that found other evidence for this missing matter. But her work was really like the beginning of when the whole astrophysical community said, okay, we really need to figure this out. This is really there. It's definitely out there. And it was this incredibly strong evidence that dark matter was a major component of the universe. And a lot of people feel that her work should have been recognized with the Nobel Prize because it did really change our outlook on the universe.
It really was.
Let me add that this is exactly what you do in experimental physics. So it's not needed that you have a theory guiding you to do something. You just observe. She was not having anyone asking her for dark matter. She was just observing the universe as an experimentalist and say, okay, there is something wrong. Let's try to understand what it is. So it's like what we do. You try to have evidences of something that is not what you expect. And on this, then you can build some theory then, or you can move really a step forward. So to answer to the guy saying that this is not useful, we have to say that we moved from medieval age to our known age because we tried to be, we still have curiosity of understanding new things. When we stop it, we do not progress anymore.
And what Vera found is not just true for other galaxies, but even in our own galaxy. So you'd expect that the stars closer to the edge of the galaxy would be moving slower, kind of like how Pluto moves slower than Earth because it's further away from the sun. But that's not what she found. And so even in our own galaxy, I mean, more than 3/4 of the matter is dark matter. So to think that it doesn't matter, I mean, it's like being in school and your teacher telling you that you didn't understand 75% of a test. I'd be pretty concerned.
I actually met Vera Rubin about 10 years ago in a panel discussion with Brian Greene. And I was really, I mean, she told me something that blew me away, was that when she made this discovery, not many people were willing to invite her to give a talk about it. I think it was Bryn Mawr College in outside of Philadelphia.
Stefan, I've got 30 seconds. Finish your story in 30 seconds. And your takeaway from that was?
Well, my takeaway from that was, how, the kind of resistance that she got when she first made this discovery.
And now she's famous forever. Thank you very much, scientists Mauro and Katie and Stefan and Alex. We really appreciate you coming and bringing science to the stream. Malika, how's this conversation been going?
Very well. I think our audience learned a lot, but I'll end with this tweet on Vera. This is Yuna, who says Vera Rubin's seminal work was incredibly important. She was a pioneer in dark matter research, and her work forms the basis on which a huge community of researchers builds today.
Dark matter matters. Thank you, everybody. It's been good to have you on the stream. See you next time.